Hey guys, good morning. In rocket and missile subject, today we are going to see about forces, moments, and acceleration acting on a missile vehicle passing through atmosphere. We are focusing that our missile is passing through the atmosphere, not in the space, right? So in this, we are going to calculate force and moments with respect to the missile which the operating at the various atmosphere, right? So force equation and moment equation we are going to calculate. So let us draw the diagram, schematic diagram of this missile, where the components of forces and moments acting with various location, right? So this is our missile body, and we are drawing a horizontal local horizon or reference line. With that, this is the CG where the entire load take place, and the flight path of this missile is with respect to the local horizon is theta, and the angle between the reference or reference axis of the missile and the flight path, which is called the angle of attack, or which is called this is the freezing velocity we will get, right? So we have the fins or control unit, that we have the beta angle of angle between the reference axis as well as the controls or the body axis, right? Let us consider body axis. And CG, we have the different components. Lift components, we have different cases. For example, nose lift, we have nose will produce a separate lift, and a body will produce a body lift, tail will produce a tail lift, right? So each component will produce different lift, and we have the resultant lift. We have the combination of nose, body as well as tail section, right? So we have the normal force and chord-wise force. This is chord-wise force C, and normal force NZ. So this force is called NZ into weight, right? So we have the another force, thrust force we have, right? These are the forces which acting in a particular case where all the forces and moments include during the vehicle passes through the atmosphere, right? So we have angle of attack. Alpha is the angle of attack. The beta is angle between control surface and body axis. LV is a normal component thrust vector, right? This is LV is a thrust vector of the entire missile. So again, coming to the LN equal to nose force vector. LR is the resultant of the entire missile, resultant normal forces. F is the thrust along the longitudinal direction. So we have to calculate the stability part or the missile passing through the atmosphere, both longitudinal, lateral and directional axis, how it is responding in individual axes. So here we are focusing on thrust along the longitudinal axis. Thrust is along the longitudinal axis. So LT is a normal force due to the total surface or tail surface. So tail will also produce a lift. So we have to add that lift to the resultant force. So we have LB is a body force vector, and weight is the entire weight force acting in the missile. C is the chord-wise force, or else we called as a drag force. Drag is different for this missiles. We will see about that in later. So here, so again NX we have in this diagram. In this diagram, NX and NZ will be there. This NZ and NX will be there. NZ and NX will be there. This will be load factor in longitudinal and transverse direction. X direction is a load factor in longitudinal axis. Z is a transverse direction axis. So F is a force along the longitudinal axis. Cn is a normal force coefficient. So we calculating everything in terms of coefficient. So we are focusing Cn equal to normal force coefficient. So D, the missile body diameter. This is very important. So just think that the importance of the diameter of missile body is very important. Let us take this missile, right? So this is the missile body diameter. So this three portion, cone, body and tail section. This is a nose portion, this is a body, this is a tail. So each one will have the lift, it will produce a lift. Based on the CG, we have W. Just consider whenever you solving the problem or the deriving thing, you have to include all the factors which influencing in the flight or in the real case. So we have to get the D from missile body diameter. Q free stream dynamic pressure, we will call as Q equal to the dynamic pressure of rho V square. Half rho V square is the dynamic pressure over the, definitely due to this free stream velocity, the entire body get dynamic pressure. And we always know so we will see the in stability and control, we see in that CL versus alpha curve. Similarly, here we also see a normal forces, coefficient of normal force with respect to angle of attack, we will see as a slope of the curve, which is Cn versus alpha. Right? So here we have to calculate from the diagram. From the diagram, you have to calculate what are the resulting force, horizontal force, or with respect to the resultant force, what are the forces are acting with this parallel. So this is lift force, which is normalized load factor into weight. This is the main thing you have to calculate. So and we can also the resultant is due to the nose, body, tail and velocity vector, right? So we have the normal component due to the thrust vector. These are the four components. Lift is the resultant vector. We have to include all the nose lift, body lift, tail lift, as well as the thrust vector of the normal component. These are the we have to include for the entire resultant lift coefficient. So summation of the longitudinal axis, we have to add the longitudinal axis forces. So we have F equal to chord-wise force plus resultant lift. So resultant lift in terms of NXW. So right, we have C plus NXW is the resultant force along this longitudinal axis. So we calculate lift and forces. Now we have to calculate if M0 is a moment about CG. So now we are taking moment about the CG point. So moment about the CG point. Definitely moment, this is moment about CG point. So we have nose momentum, body momentum, tail momentum and the thrust momentum, this thrust momentum. So resultant momentum we have to calculate. Similarly for the lift momentum, lift force. So M0 equal to Mn, nose momentum, body momentum, tail momentum and vector momentum, thrust vector momentum. So these are the momentum acting in with respect to the CG. Now we have to elaborate this lift forces as well as the momentum forces to get the better exact expression for the lift value and drag value and the moment value, as well as the what is the influencing the angle of attack, as well as the beta, alpha and beta. Beta is the angle between the controls. If the control surface is operated, how it is influencing in flight or in the missile in flight condition, flying condition, right? So further, since the aerodynamic forces are expressed as, we know L equal to half rho V square A into CL. This is the formula we know for lift value. In this we have lift. So half rho V square is a dynamic pressure of Q. We can represent as a Q. And A will be the surface. We can also write it as a S. CL be CL. So for our case, we have to calculate for the all nose, body and tail, as well as the vector thrust vector component. Thrust is a different component and nose, body, tail is different component. So these things are influencing in different manner. So first we have to calculate Ln, Lb, Lt is half rho V square. This is A square. Instead of A square, we are using area is D into D square. So we are getting D square, so that we are getting area as D square. So CL, so we cannot say directly the CL is influencing directly lift coefficient. Here we have two things. One is alpha and beta. So for that alpha you have to represent it separately. Beta you should represent separately. So alpha it is dou Cn. This CL with respect to nose, body and tail, it is d Cn by d alpha. That means differentiation of normal lift coefficient with respect to angle of attack for each case, nose, body and tail into angle of attack. Whereas LV equal to same, this is half, this Q will be half rho V infinity square D square. Similarly, dCn by d beta will come for the thrust vector. So this is due to influencing of beta, here alpha and beta. So you have the lift in two cases. So lift will vary based on alpha and we can write it as L equal to CL. This is what we are deriving here. This is Q of rho V infinity S into this CL. CL we are writing into dCl by d alpha into alpha. For beta, dCl by d beta into beta we are writing. So lift we are getting this equation. This is equation number 3 we can get for the lift value. Now we have to find out what is the resultant lift so far we identified. So as earlier we said that LR is equal to NZ into W. So we are resultant lift equal to NZ equal to W is equal to, for nose we are writing dCn by d alpha for nose, dCn by d alpha for body, dCn by d alpha for tail. So this is the lift coefficient with respect to alpha, d square area into half rho V infinity square V square. This is for dynamic pressure. This is for nose, body and tail. So plus we need to add the vector components. dCn by d beta is due to the vector component into beta d square q. This is dynamic pressure. So we identified lift. The resultant lift is acting in a missile is entirely depends upon the nose, how much lift coefficient produced, the nose lift, body lift and tail lift. With respect to how much dynamic pressure is acting, especially the d square, what diameter does the missile is having and what angle of attack it is flying. It is in addition to that, it is also to consider the importance of the how much control surface of the fins or the missile body you are fixing, in which angle it is acting to the surface or the reference axis. That thrust will indicate also important, and this tail portion produces a dynamic pressure over the tail section, that is Q. This is at the diameter of the entire missile. So we calculated resultant lift LR equal to NZW is equal to nose, body, tail lift, and the similarly for the vector component which is produced in the tail section. Alright. So similarly we need to calculate moment M. So this is the next component we are going to calculate. M equal to what we know? M equal to force into distance. We have, this is the lift force. Lift force into distance, we have the diameter of the missile. So here we are calculating, already we have the entire lift force. So this is normal dCn by d alpha alone. We are not going for a beta. Primarily we go with alpha and then we add for the beta overall moment. Here the only term is same lift force, same entire term will come, this entire term will come, and you have to multiply with the d, the distance. So the resultant lift we have to use and you have to multiply with the d. So resultant lift we have the entire term dCn by d alpha. We can write as n nose, body and tail. We are simplifying in this q d square into d. This d square into d q will come alpha, for this for alpha. For beta you need to write this is beta. dCn by d beta q d square into d into beta. So d cube will come. So you have to split for each term. M equal to dCn by d alpha into n plus dCn by d alpha for body, dCn by d alpha for tail into q d cube alpha. That is very much important, and same, this formulas are same, only the term is bearing is d cube plus dCn by d alpha into v q d cube, this d cube for beta. So this is the moment equation for the missile. Now we are going for the what is the trim condition. What is the trim? We are seeing in stability and control to balance the unbalanced moment, to rectify it, to solve that, to make it to become an equilibrium. We are adjusting the trim condition. If you change the small portion of that trimming value, that makes the flight or the vehicle or the missile or aircraft making in a stable or equilibrium condition. So at trimming condition, moment with respect to that point will be 0. Moment at CG is 0. So moment is m not equal to 0 at trimming condition. So this is important key you have to remember. So m equal to 0 at trim condition is equal to, you have to equate with this equation equal to 0. Then dCn by d alpha into nose, dCn by d alpha for body, dCn by d alpha equal to tail, q dq by alpha plus dCn by d beta for thrust vector, q dq into the control surface angle. This is beta. Now we are getting dCn by d alpha, and you are taking into this next to the equation, and this in terms of minus. So you are cancelling this dynamic pressure QQ, surface volume of the dq, volume of the missile dq by dq. Only the term alpha and beta will be there. So you are keeping this alpha here and getting this value down. Alpha by beta is equal to minus of, this is very very important, I will say why, minus dCn by d beta for the vector component divided by dCn by d alpha nose, body and tail. So this is the trimming equation, trim condition or trim equation. If you want to trim, to maintain an aircraft at a zero moment in the trim condition or equilibrium condition, you have to consider what angle of attack the missile is flying and what angle of attack does the control surface is deflected or it is happening. I already told in the stability in control, the rate of change of lift coefficient with respect to angle of attack dCl by d alpha is always less than 0. Then will be due to stable flight. Similarly, to maintain this aircraft, you have to maintain alpha by beta is always less than 0. That means it should be negative, always negative, right? So this entire components is influencing only because of the alpha and beta, right? This is the equation for the trim condition. So let us recall the entire term for the force and moment and trim condition for the missile flying in a passing through atmosphere. So we have drawn this missile body and we have included all the force and lift and drag, normal force, angle of attack, theta, control surfaces. So control surface angle we have added every components in this diagram, and the angle of attack alpha, beta the angle between control surface and body axis, L is the normal component thrust vector, Ln is the nose force vector, Lr is the resultant normal force vector, F equal thrust along the longitudinal direction, Lt equal normal force due to total surface or tail surface, Lb is a body force vector, W is a weight force, C is a drag force. So these all things are acting here. Nx and Z are the load factor in the longitudinal transfer direction. F equal to thrust along longitudinal direction. Cn is a normal force coefficient. D is a missile body diameter. Q equal to free streak dynamic pressure over the missile. dCn by d alpha is the slope of the curve. Plotting between the Cn and alpha. CL versus alpha you curved for the airfoil, no, similar to that. So resulting lift force is Lr equal to NZW. So we are calculating lift. So we also similarly we are calculating momentum for all nose, body, tail and vector. So that is what we are getting resultant lift vector in terms of alpha and beta. Similarly for adding momentum we have to calculate force and distance. The same thing will come, and distance will diameter will be added. So this is the moment equation. For trim condition, m equal to 0 moment with respect to dynamic center, or Cg equal to 0 for trim condition. M not equal to 0, you are equating with this equation, and you are getting equation, and we are calculating the same similar terms, and we are getting in terms of trim condition in terms of alpha and beta. Alpha by beta is equal to the ratio between alpha and beta, which influencing the velocity vector which is produced by the missile, the entire lift coefficient produced by the nose, body and tail, right? So this is what we have studied in this lecture. So next class we will see the longitudinal effect of missile, lateral effect of the missile. We will do the calculation for that, right? Thank you.